This is section 5.6, the real zeros of a polynomial function. Our objectives for this section are going to be the following. We're going to use the remainder and factor theorems. We're going to use the rational zeros theorem to list the potential rational zeros of a polynomial function. We're going to find the real zeros of a polynomial function, and we're also going to solve a polynomial equation. So I meant for that to be an objective too. It just didn't get indented there when put into the list correctly. All right, our first theorem, the division algorithm for polynomials. I'm going to use an example to help illustrate this theorem, because sometimes when we look at theorems or we look at definitions, they're kind of abstract and they're kind of hard to make sense of. But when we use an example, it just makes so much more sense. So the division algorithm for polynomials says if f of x and g of x denote polynomial functions, and if g of x is a polynomial whose degree is greater than 0, then there's a unique polynomial functions q of x and r of x for which f of x divided by g of x is equal to q of x plus r of x divided by g of x, or f of x is equal to q of x times g of x plus r of x. So if you notice over here on the side, what I'm doing is I'm using some long division of polynomials to divide a couple of these polynomials here that I wrote out as f of x and g of x, and I'm going to come up with a q of x and an r of x divided by g of x. So if you look at this polynomial division that I have here, my remainder ended up being the number 3. Since I have a remainder, I'm going to write that remainder over the divisor. So I'm going to write plus 3 over x minus 2. So if you look at this, the x squared plus 4, that's the q of x part. That's our quotient. The 3 over the the 3 over the x minus 2, that's our r of x over our g of x. Okay, so see I think that makes a lot more sense. Now let's look at this or part here. So if I wanted to just rewrite this in a slightly different way, right? I could rewrite this as the dividend is equal to the quotient times the divisor, and then I would add the remainder. And this is what we would normally do to check like our long division on a polynomial division. We would do this step process here to check it. So this part that I'm boxing in on the right, that's the part you do to check your work for the top problem. You would multiply the divisor with the quotient and add the remainder, and it should come out to your dividend. So hopefully this example here, writing it out this way, hopefully it makes more sense now what all of these, I know when I'm writing out all these functions here, you're like kind of like, what does all this mean, but when you see an example like this, hopefully it just makes more sense, right? And of course all of this is true where r of x is either the 0 polynomial or a polynomial of degree less than that of g of x. Remainder theorem. Suppose f is a polynomial function. If f of x is divided by x minus c, then the remainder is f of c. Now, what I'm going to do here is I'm going to do a little bit of synthetic division to show you another way to do this, because this gives you a sense of seeing that factor, that x minus c part that you see in the remainder theorem. Kind of just helps it make more sense, right? Because in synthetic division, when you use synthetic division, right, it has to be of the form x minus c in order to use synthetic division. So if I were to use this x minus 2, the c would just be the 2 part. So I would use this 2 as my c. And another way I could find the c is I could set the x minus 2 equal to 0, and I could solve for x. And that could be another way for me to find my c if I'm having trouble like writing it in that form, that x minus c. So I would write the 2 here apart over here to the side. Actually, first let me write down my dividend, because I want to make sure that when I use synthetic division that I write out my dividend and that it's in descending order, and then I'm accounting for all the coefficients. Even if it doesn't have one of those terms, if it's missing like an x squared term, I still need to account for it with a 0 coefficient. So this is how we do synthetic division. Hopefully you guys remember this. And this would provide me with the answer as well, if I use synthetic division. Same answer, just a slightly different way, right? But it allowed me to talk a little bit about that x minus c term in that form that it has to be in when we're using synthetic division. So in the remainder theorem, what it basically says here, if I had, suppose f is a polynomial function. If f of x is divided by x minus c, then the remainder is f of c. So the remainder in this case, if you notice the remainder, it's 3. So basically it was saying that if I had taken that 3 and I had just, if I wanted to find just that 3, I could have just found f of 2 and it would have given me that 3. So in this case, our f of x was x squared minus 2x squared plus 4x minus 5. So let's say I say, okay, I want to know what f of 2 is. I plug in a 2 every time I see an x, and I simplify it. And then this is when it simplifies all out. If I did everything correctly here, right, this should come out to 3. F of 2 equals 3. And that just happens to be the exact same thing that I got in my remainder, whether I did synthetic division or whether I did the long division. So that's pretty cool, right? That's called the remainder theorem. The factor theorem. Suppose f is a polynomial function, then x minus c is a factor of f of x if and only if f of c is equal to 0. All right, so here I did not get f of c is equal to 0 in this last example, so I can't use this last example to refer to. But basically it's saying if your remainder is a 0, right, and then you've got this x minus c as a factor, then of course then f of c would end up being 0. So there's 2 things that come as a result of this, right, that we can deduce from this. Well, number 1, if f of c is equal to 0, then x minus c is a factor of f of x, right? And number 2, if x minus c is a factor of f of x, then f of c is equal to 0, right? I know it sounds like pretty much the same thing, right? It's pretty much the same thing, right? Just reversed. But yeah, this is what we can deduce from this if from the factor theorem, right? All of this stuff that we've been talking about here is important, right? So ultimately, everything that we've mentioned here, you should have this stuff memorized, right? But you should ultimately really understand it as well, not just do meaningless memorization, but just try to understand why, all this is true, and how it connects, so it makes more sense when you're memorizing it. All right, use the remainder theorem to find the remainder when f of x is divided by x minus c. Then use the factor theorem to determine whether x minus c is a factor of f of x. Write f of x in factored form. Okay, so first of all, I want to apologize here because this problem says number 4, and it's our first problem for this section. So if you want to cross out that number 4 and just write a number 1, that's perfectly fine. Let's go ahead and do that. All right, so my factor here, they're giving me x minus 2, so the c in this case is going to be c equal to 2, right? And if I solved it, if I said this factor equals 0 and I solved it, and I would get x is equal to 2. That's another way, if you can't tell, because I know sometimes people look at this and they're like, they want to write down a negative 2 because they see a negative 2 there. But that's not your c. The c is just a 2. It's what's going to give you the 0 in that factor. That's what your C is going to be. So if I plug in a 2 into this function, if I find f of 2, we're trying to see if this is a factor. If it's a factor, then it's going to be equal to 0. If it's not a factor, it'll be equal to any other number that's not a 0. And I get f of 2 is equal to 0. So therefore, what does that mean? Yes, that means that this, we have a remainder of 0 from the remainder theorem. That's what it states. And it also states that if you have a remainder of 0, and if your f of 2 is equal to 0, then that means that the 2 is going to be a 0. And that your factor, one of the factors of this function is going to be that x minus 2. So it is a factor then, therefore. So we found the first part here where it says find the remainder when f of x is divided by x minus c. The remainder was 0, and that comes from the remainder theorem up above that we just did. We were just talking about that. And the answer then to this would be yes, x minus 2 is a factor of f of x. The next part is we need to write this in factored form. Okay, so there's more than one way to do this part for this particular problem. So it just depends on, I would just say which way calls out to you, which way seems easier for you. With a lot of these problems, you got to choose the easier way. I'm going to use synthetic division. So I'm going to rewrite this. So I'm writing the coefficients, I'm making sure it's written in descending order, and I'm accounting for all the terms, even the terms that aren't shown, like the x cubed. I'm going to put a 0x cubed term, and for that 0x to the first, I'm going to make sure I put that 0 there. All right, bring down the 4, multiply 4 times 2 is 8, 0 plus 8 is 8, 8 times 2 is 16, negative 15 plus 16 is 1. And 0 plus 2 is 2, and 2 times 2 is 4. Negative 4 plus 4 is going to give you 0. So therefore, yes, 2 is 0. We already knew that. But what we really wanted out of this is we really wanted to get this polynomial that we would get from dividing it by x minus 2. There is my polynomial. So I know that this polynomial, if I were to multiply this polynomial with the x minus 2, I would end up with that function, the original function. So x minus 2 times this polynomial is equal to our f of x. These are factors of our f of x function. We're going to try now to continue factoring that function because the, that's what we want to do. The x minus 2, I don't want to worry about it, so I'm just going to draw an arrow with it coming down here. I'm going to focus on just that polynomial with 4 terms, and I'm going to try doing factoring by grouping. I can factor out a 4x squared, and that's going to leave me with an x plus 2. I can factor out a 1 from the second one. That's going to leave me with an x plus 2. I can factor out an x plus 2, and that leaves me with 4x squared plus 1. So it looks like I got this factored out pretty well. All right, great job. I did pretty good here. So let's go ahead and write this. This is what f of x is equal to in factored form. So I'm going to write down here f of x is equal to all of these 3 factors. And this represents the factored form of f of x. Now, I had said earlier that there's more than one way to have done this problem, right? This particular problem, we could have done it other ways as well. Another option would have been to do the long division process. And if I would have done the long division process, it should still give me the exact same answer, right? If I did everything correctly here, it's got to come out to the exact same thing. So I'm just going to set it up here so you guys can see that this would have been another option for you to have done. Let's say you forgot how to do synthetic division. Say, I forgot the process. Then you can use long division, and this works. Okay. Another option for this particular problem, the 4x to the fourth minus 15x squared minus 4, it's actually of that form, that ax squared plus bx plus c. And this one actually factors out, right? So I could have factored this out, right, using my magic x and then creating this into a factoring by grouping problem. And then factoring out the GCF of each one of these. So I end up with these factors, but then I have the difference of two perfect squares, which factors into x minus 2 and x plus 2 times that 4x squared plus 1, which is the exact same factors I had gotten earlier using the synthetic division. So just trying to show you more than one method that you can use, and it's good to know more than one method, just in case you forget one of the other ones, or if you want to double check your work, right? Am I right? Yes, I'm right, right? So, yes, this is what we would do here for this problem. All right, let's go on to the next one. So for this next problem, I really wanted to keep practicing what we did in this last one. I know there was a minus here in your notes handout. Let's change that to a plus here for this problem. Because then we can practice using some of the techniques we were just talking about. Otherwise, if we leave it as a minus, then it turns out that this x plus 1/3 is not a factor, and we really can't do too much with the problem. And I want to be able to do a little bit more. Okay, so what we're looking for here is we're looking for the c. If I want to find the c in this particular problem, I need to rewrite this as x minus c. So I would need to rewrite this as x minus a negative 1/3. Therefore, my c is equal to negative 1/3. Another option, set x plus 1/3 equal to 0 and solve, and you'll get x is equal to negative 1/3. So that's what we're going to use as our c. In order to check and see if this is a factor, I'm going to find f of c, or f of negative 1/3. If I get a 0, then that means this actually is a factor, that x minus c part. Now, when you're doing this process, instead of doing it all by hand, you got a calculator. I think it's easier to just plug this into the calculator. So I would just go ahead and plug this into your calculator and get your answer. So this should come out to 0 when you plug this in. Maybe I should show that step right here about how we got that in the calculator. Okay, so if we go to your calculator, we can go ahead and type in that function as y sub 1. So that's what I'm doing. I'm typing in that 3x to the fourth plus x cubed plus 3x plus 1. Now, if we go to vars, y sub 1, I can put in some parentheses and I can evaluate this function for any specified value of x. So I'm going to type in that negative 1/3, close the parentheses and press enter, and there you go. So that basically tells me that f of negative 1/3 is 0. So negative 1/3 is a 0. So going back to our problem over here now that I'm, I worked it out and I'm positive that this negative 1/3 is a 0 and that x plus 1/3 is a factor, I can now go ahead and, I can factor this out, right? So I could have divided, I could have done some synthetic division to make this look a little easier, but I think it's easier if we just do factoring by grouping to factor this function out. Just because of that negative 1/3. Now this isn't always going to happen where it's going to always be factorable like this one in this case, but sometimes it is. It's good to look ahead and say, hey, is there an easier thing I could do instead of having to divide this out? Now that x cubed plus 1, I hope you guys realize that that was the sum of 2 cubes and that we could factor that out. So just in case you didn't catch that, let me just quick reminder. This is the sum of 2 cubes, and you guys should know the formula for factoring this out. A cubed plus b cubed is equal to a plus b times the quantity a squared minus ab plus b squared. Just in case, you didn't know it. If you didn't learn it, the first time around when you learn factoring, it's never too late to learn it. All right, so I have completely factored out the function. And I also found out that remainder that it was asking me for, it might have looked a little nicer if I had written, yes, that x plus 1/3 is a factor. That might have looked a little nicer if I had written it out that way. And then this is the factored form of the function. So there, I think that was all that this problem was asking for. All right. So that was a good problem, huh? What did you think about that one? That was good, right? All right, let's go on to the next theorem, the theorem of the number of real zeros. It says a polynomial function cannot have more real zeros than its degree. So if you look at the degree of a polynomial, you know that's the maximum number of zeros that it's allowed to have. Let's use this function as an example. Look at this degree. It's degree 3, or a third degree function, third degree. So because it has a 3 in the exponent, that's the largest exponent for these variables, that means the maximum number of zeros, of real zeros, is going to be equal to 3. All right, so that's basically what that theorem says. All right, let's go on to the next theorem, the theorem of the rational zeros theorem. Let f be a polynomial function of degree 1 or higher of the form f of x is equal to a sub n times x raised to the n plus a sub n minus 1 times x raised to the n minus 1 plus so on, plus a sub 1x plus a sub 0, where a sub n is not equal to 0 and a sub 0 is not equal to 0, where each coefficient is an integer. If p divided by q in lowest terms is a rational zero of f, then p must be a factor of a sub 0 and q must be a factor of a sub n. So the p here is going to be factors of a sub 0, and that's always going to be the number that's in the back when you write it in descending order, your constant. And the q must be a factor of a sub n. So it's basically, when you have it written in descending order, it's going to be the leading terms, right, coefficient. The leading coefficient. You're looking at that number to get all the factors of it. And that's basically what q represents. It represents all the factors of a sub n. And p's the factors of a sub 0. All right, let's go ahead and use this and see if we can find the list of potential rational zeros for this next one. So this next problem says, first, determine the maximum number of real zeros that the polynomial function may have and list the potential rational zeros. F of x is equal to 6x to the 4th minus 6. I meant f of x is equal to 6x to the 4th minus x squared plus 2. The maximum number of real zeros is going to be the degree of this function, which is, it's a 4th degree. So that means the maximum number of real zeros is going to be equal to 4. That's the most that it could possibly have, the most real zeros. All right. Now that we've got the maximum number of real zeros, we're ready to find the list of the potential rational zeros. We're going to use the rational zeros theorem. So why don't I go ahead and I look at this function and determine what are going to be the factors of a sub 0 and what are the factors of a sub n. First thing, and very important, descending order. It just makes it easier to identify which one is going to be your a sub 0 and which is your a sub n. This is our a sub n. So remember that's associated with the q. So q, right, must be a factor of 6. And we're basically going to try to come up with every single factor of 6. And 2, that's your a sub 0. So this represents the p, or p, I should say p must be a factor of 2. So you're going to list out all the factors of 2, and that's going to represent your p values. Now, the way I remember it is I always think to myself, p always goes in the back. And that's what I used to remember this, and it works for me. But whatever works for you, right? Factors of 2. So that's going to be, when you write this quotient, or I should say this ratio, make sure you write the p on top. Think maybe alphabetical, maybe if that helps you. P goes on the top. So I'm going to write the factors of 2 on the top here. And for the factors of 6, I'm going to write those on the bottom. And I've got to take into account positive and negative numbers. So when I'm thinking of the factors of 2, I'm going to write positive and negative 1 and positive and negative 2. Those are all the factors of 2. For 6, I'm going to write positive, negative 1, positive or negative 2, positive or negative 3, positive or negative 6. Now that we have all of those written out, we're going to write down all of the possible ratios you could get with these numbers. I need some more space here because I can already tell I'm not going to have enough space. How about I insert some more space in between these 2 pages so that I can have more writing space? That looks better. Okay, so now we're listing out all the possible ratios you could possibly have. Now I'm going to take my time here to really explain this. This is going to be plus or minus 1 over plus or minus 1. If you divide 1 by 1, right, we're going to get 1 over 1. And it's still going to be positive or negative. So I'm going to write positive or negative 1 over 1. If we simplify that, it's going to simplify to positive or negative 1 because 1 divided by 1 is 1. All right, let's go on to the next one here. So now I'm going to have positive or negative 2 over positive or negative 1. So that's going to be positive or negative 2 over 1. And if I simplify that, that's positive or negative 2. All right, so we have managed to do everything with a denominator of 1. So now we're going to move on to the next denominator. I'm going to do everything here in the numerator with a denominator of 2. So this is going to be positive or negative 1 over positive or negative 2. And that just is going to be positive or negative 1/2. That's already simplified. So I'm just going to copy that one down as it is. So that's going to just be positive or negative 1/2. Let me see if I can get rid of this number 19 here for the page number. It's just bugging me because I'm trying to list out my answer here and it's in the way. Okay, now we're going to go on to the next one. We're going to go positive or negative 2 over positive or negative 2. So if I write positive or negative 2 divided by positive or negative 2, I'm going to get positive or negative 2 divided by 2. But that's just positive or negative 1 when you simplify it. So I'm not going to recopy that one in my list because I already have positive or negative 1 in my simplified answers. Okay, so that's already accounted for. We don't need to copy it down again because we already have it. All right, now positive or negative 1 over positive or negative 3. So that would be positive or negative 1/3. And that's already reduced, so I'm just going to copy that down. All right, next one. Now we're going to put positive or negative 2 over positive or negative 3. That's going to give me positive or negative 2/3. And once again, that's already simplified, so we're just going to copy that down. And I think we're ready to go on to our last number here in our denominator, which is this positive or negative 6. So positive or negative 1 over positive or negative 6 is just going to give me positive or negative 1/6. And that's already reduced. And the very last one here is going to be positive or negative 2 over positive or negative 6. Now, if you take positive or negative 2 over positive or negative 6, and you get positive or negative 2/6, and you reduce that, you get 1/3, but we already have positive or negative 1/3. So I'm not going to copy that one down again. It's already there. So looking at these, I know it looks like we have only 6 answers in our final answer list, but this is actually 12 answers. I want you to know, because every positive or negative, when you have a positive or negative, remember that's actually 2 numbers there. Okay? So this is my final answer here for my list of potential rational zeros. And yeah, maybe I should write this out like steps that I took to do this problem. What do I call this step 1 here? So step 1 was basically just all the factors of the P and the Q. Step 2, we basically listed out, or we formed all possible ratios of P divided by Q. And then the very last step, we only wrote down like all the simplified answers. So we basically simplified all the possible ratios that we found. And we weren't redundant. We didn't repeat ratios, but we only kept one set for each one. So this basically, what this is saying for our final answer, it's basically saying if f has a rational zero, it will be found in this list of 12 possibilities. So once again, I just want to remind you that's actually 12 numbers there. I know it looks just like 6, but when you put a plus or minus in front of something, it turns it into 2 numbers. All right, let's use the rational zeros theorem to find all the real zeros of each polynomial function. Use the zeros to factor f over the real numbers. Rational zeros theorem, we talked about that earlier, right? And we just used the rational zeros theorem right now to list all possible rational zeros. And then use the zeros to factor f over the real numbers. Now, I'm going to be honest with you guys. When I'm looking at these problems, you know, sometimes I ask myself, what's the easiest way to go about doing this? And I know if they're asking you to do it a certain way, yeah, I can understand you're supposed to do it that way. But some of these problems can get very long, very tedious. For this particular problem, I'm going to try factoring first to see if I can get the zeros that way first. And then afterwards, I'll list out all the list of potential zeros, you know, for you guys. But, you know, sometimes, you know, I just feel like if I can get to the answer a little bit faster, like have a better understanding of what's going on, it might be better for me. I'm going to use factoring by grouping to see if I can try to factor this polynomial out using the factoring by grouping method, because it's got 4 terms. And I can see here now, yes, I could do factoring by grouping. I can factor out that x plus 2. And then now I notice that there's actually a factor of 3 that I forgot to factor out here. So I'm going to factor that out. Put that 3 in the very front. Now here, I see x squared minus 5. And now we need to talk about this x squared minus 5 here, because in the instructions it said, use the zeros to factor f over the real numbers. Real numbers, well, real numbers include irrational numbers, right? So that 5, I know normally when we learned to factor, we would have said, oh, I can't factor that anymore because, you know, that might have been the difference of 2 perfect squares, right? If 5 had been a perfect square. But now, guess what? Now we can actually pretend like that 5 is a perfect square. And we can actually factor this. So remember the difference of 2 squares. We had a formula for factoring that out. That said, if you had a squared minus b squared, that's equal to a plus b times a minus b. Remember that? And 5, if you wanted to think really hard about this, if you wanted to say, is there a number, any real number, that I can square and will it turn into a 5? Now, if you're including the set of real numbers, there is a real number that you can square, right? Because we can now include irrational numbers. The square root of 5 squared is equal to a 5. So technically, 5 is kind of like a perfect square if you're talking about including the set of real numbers right in there, not just rational numbers. So I could rewrite this as x squared minus the square root of 5 squared, and then this should factor into x plus the square root of 5 times x minus the square root of 5. Wow, that's pretty cool, right? So I'm going to actually factor this out. So here we go, x plus the square root of 5 times x minus the square root of 5. And if I were to multiply that out, yes, that would turn into the x squared minus 5. Now, I can find the zeros by setting each one of these factors equal to 0 and solving each one of these. Now, I like to show every little step, right? If you don't need to show every little single step, and if you could go straight to the zeros without having to write these steps out, then that's fine. But I do it for the people that need to see it. I always feel like I'm trying to help out the people who are the most lost, you know? So now that I got my zeros here, I technically have found what they were asking for, right? They said, find all the real zeros of the polynomial function, right? And use the zeros to factor f over the real numbers. I actually have factored f, and I have found all of my real zeros. Isn't that cool? Let's write out our answer. Real zeros are going to be, we got -2, we got negative square root of 5, and we got positive square root of 5 for our real zeros. So we're going to box that in. And I'm also going to box in the factored form of f of x because they were also asking us to factor f over the real numbers. So I want to make sure I also box that answer in as well. Okay. Now let's go back to what it had originally asked us. It had originally asked us to use the rational zeros theorem. But you could see here that, if I had used the rational zeros theorem, I might not have gotten right away to the factors as I did this way. I think this way was a much faster way of getting to the zeros and getting to the factored form of the function. But let me just show you that method if you wanted to go about and say, I want to use the rational zeros theorem, right? Or I need to show it because that's what my professor asked for and I need to show that step. You would use the rational zeros theorem. So we would need to write down all of those possible ratios of P divided by Q. So I'm going to make sure I know what those factors of p and q are. My function was f of x is equal to 3x cubed plus 6x squared minus 15x minus 30. So my a sub n was 3. My a sub 0 was negative 30, but we don't really need to worry about the negative, you know, because the 30 is what we need. We're going to put plus or minus in front of it anyways. So I'm going to have q here. I'm going to write a q over the 3 and a p over the 30 just to remind me. I'm looking for those, for every factor of those coefficients. Let's start off with p, all the factors of 30. Okay, so that there's a few there. I got plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 5, plus or minus 6, plus or minus 10, plus or minus 15, plus or minus 30. Wow, a lot of factors. And for our q, we got plus or minus 1 and plus or minus 3. If I write out all of the different possibilities that I could write out these ratios, and why don't I just go ahead and write them straight into the simplified form so I don't have to do like all of these. So first one, I'm going to just divide all of these top numbers by 1. So I'm just going to basically copy all my numerators. And then for the second one, I'm going to divide them by 3, but I don't want to repeat the ones that I already have written down. So I'll try to be careful here. So I'm going to have plus or minus 1/3, plus or minus 2/3, plus or minus, that's going to be a 1. I'm not going to repeat it. Let's do plus or minus 5/3. That's going to be 2, so I'm not going to repeat it. Let's go to plus or minus 10/3 then. And let's do plus or minus, that's going to be a 5. 15 divided by 3 is 5, so I don't want to use that one. And then last, 30 divided by 3, that's a 10, and I've already got it. So I think I'm done. I think that's it. What do you guys think? Once you got down all of these possibilities for zeros, then you would have to go through and plug them into the function to see which ones give you remainders of 0, right? So you'd have to do like f of 1. Is it equal to 0? It would have been no, right? F of negative 1. Is it equal to 0? That would have been a no. F of positive 2. Is it equal to 0? That would have been a no. F of negative 2. That would have come out equal to 0. So you would have known that that would have been a 0, and then that would have created your first factor. So you could have gone into doing either synthetic division to try to come up with the next polynomial once you start factoring out the original function, right? So that would have been the process you would have used if you had done the rational zeros theorem way. And I just think it would have been a more tedious, a longer process. Now, sometimes we have to use the rational zeros theorem way, because I know you're thinking, well, then I don't even need to know this, right? Professor Olivas, why do you have to even bother learning this? Well, look at this polynomial. I've got 5 terms. I don't know how to factor this. I have to use the rational zeros theorem. So we are forced to have to use the rational zeros theorem. Let's go ahead and figure out what are going to be all our factors of our a sub n and our a sub 0. So all our possibilities for our ratios for p divided by q. So remember, p always goes in the back. Factors of 8. I'm going to have for the factors of 8, I'm going to have plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 8. All the factors of 1, oh, that's nice, plus or minus 1. So this is actually a much nicer problem than the last one in setting up the rational zeros, the possible rational zeros. I'm just going to have plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 8. So now we go through the process of plugging them into the function and seeing if we get it to equal 0. That means we'll have a remainder of 0, which means we have a factor that divides evenly into this. F of 1. So I would just, once again, use your calculator here. I already showed you how to plug this into the calculator. I don't want to have to show you again. I'm just going to do it on my own with the calculator, and you guys are going to do it with your calculator. And over here, I'm just listing out all the different possible rational zeros we could have, but I'm actually listing them all out so you know that there's actually 8 possible rational zeros here. All right, let's plug this in. F of 1 into your calculator and see what you get. All right, push pause and do it on your own. I will show the setup for this, but hopefully you guys can do this in your calculator and not have to work it all out by hand. I think I'm going to actually just work it out all by hand for the people that need to see this. So I got this is equal to, I got -6 plus 4 plus 8, which gives me -2 plus 8, which is equal to 6. That is most definitely not a 0. So I would say 1 is not a real 0 of this function. Let's try f of -1. Let's see how that works. All right, so -1 raised to the 4th power is going to be +1. This is going to give me a negative times a negative. It's going to end up being a 1. But first you have to cube it, right? So it's got to be -1 cubed first, and then you multiply that -1 with the 1. So it looks like I end up with -4 minus 4 plus 8, and that's -8 plus 8, which is equal to 0. Yes! So -1 is a 0. I get so happy when I actually go through this process and I find a 0, right? Because it feels like, you know, this might be like a never-ending process. And when you finally get there, it's just a very satisfying feeling, I think, when you find a 0. If you found that -1 is a 0, then that means you found a factor of the form x minus c, where your c is equal to -1. So c minus a -1, that would be the same thing. X minus a -1 would be the same thing as x plus a 1. So x plus 1 is a factor of our original polynomial function. Isn't that cool? We can use the -1, and we can use that in terms of synthetic division. We use the 0 to find the, to try to factor out this polynomial function. So we're going to use the coefficients, and we're going to make sure they're in descending order. So that looks pretty good there. All right, so we're ready to do synthetic division now. I'm going to bring down that first 1, so bring it down. 1 times -1 is -1. -1 plus -1 is -2. -2 times -1 is +2, and -6 plus 2 is -4, and -4 times -1 is 4. We get 8, and 8 times -1 is -8. So we get a 0. These both should be zeros, right? If you got a 0 when you did f of -1, right, you got it equal to 0, then your last number that you get here from synthetic division, which represents the remainder, should also be a 0, or that means you made a mistake. So we get our polynomial that comes from as a result of this. So if I multiply x plus 1 times this x cubed minus 2x squared minus 4x plus 8, I know that this would give me our f of x. These are factors of f of x. But this x cubed minus 2x squared minus 4x plus 8 is not factored out. We need to factor it out. It's got 4 terms. Let's try doing a little factoring by grouping. Let's try it. Let's see if we can get it to factor out that way. Okay, so I can group the first 2 terms, and I can group the last 2 terms, and it looks like, yes, this is factorable by grouping. So now I see that I've also got the difference of 2 perfect squares, so that will factor into x minus 2 and x plus 2. Now I'm ready to write my function all factored out. Don't forget the factor of x plus 1 that we had in the front over here. So let's go ahead and write this over here. F of x is going to be equal to x plus 1 times, we got 2 factors of x minus 2, so I'm going to write x minus 2 quantity squared times x plus 2. So if I set each one of these, oh, I'm sorry, my laptop's a little bit, it's a Surface Pro. It's what can I say? Doesn't work with me. Well, I'm going to set each one of these factors equal to 0 to find the zeros. So once again, I like to show every little step. Some of you guys might be able to do this without showing every little step. And I'm also going to take into account that one of these factors has multiplicity too, right? That's always good to take into account, like the multiplicity of your zeros, right? Because later on, if you're trying to graph something here, you might need to use that information. So I've got x equal to -1, x equal to 2, and x equal to -2. All right, let's write that out. So this means that our real zeros for this function are going to be, we've got -1, we got -2, and we've got 2, and that 2 has a multiplicity of 2. Just want to make sure that I'm emphasizing that. We don't want to forget about everything we've learned before, right? It's all important. And you guys should know what that means when it has multiplicity 2. If a 0 has multiplicity 2, if it has an even multiplicity, it means that at that 0, the function is not going to cross the x-axis. It's just going to touch it, or it's going to kind of bounce off of the x-axis. All right, good job, you guys. That was excellent. That was a great problem. We got the factored out form of the function. We got the real zeros. We got the multiplicity here. It's awesome. It's all good. All right, I think we're ready to go to the next problem, right? All right, let's move on. Let's find the real solutions of the equation x to the 4th minus 2x cubed plus 10x squared minus 18x plus 9 is equal to 0. Now notice that this is an equation in one variable, right? Doesn't have anything about f of x on there. But it would be so helpful to use what we've learned about functions with this, right? And notice that the instructions say find the real solutions of the equations. That means you're going to solve in the real number system. That means we do not want any complex solutions that are not real. So any of those complex solutions, like with imaginary numbers, no, we don't want those answers in our final solution. So that's what it means when it says find the real solutions or solve in the real number system. Okay, so just keep that in mind. You got to be very careful when you're reading these instructions. And I've tried to teach you guys that. It's always good to reread the instructions so you understand exactly what you're trying to do here. I'm going to pretend that this is a function. Everything that's on the left, I'm going to call it f of x. So that way I can use all of my cool function rules and theorems that I've just learned about. So cool. Oh, I forgot to write the x in here. Please write an x in here for me, please. Thank you, you guys. You guys are the best. Awesome. Possum. Yes. Okay. Now that I've mentioned that I forgot to write the x and you guys are all writing in there, let's go back to the problem. Let's not try to let that distract us from our problem. We're trying to figure out when this f of x is equal to 0, or this function is equal to 0. In other words, when you set f of x equal to 0, what are you finding, right? Aren't you basically solving for x? You're finding the x-intercepts, the x-coordinates of the x-intercepts, right? Or we're looking, in other words, for the zeros, right? Because those x-coordinates of the x-intercepts, that's what we call them. We call them zeros. But visually, if it helps you to remind you that these are basically like the x-intercept values, those x-coordinates, then go ahead. All right, let's turn to the rational zeros theorem, because this is a function that's got 5 terms in the polynomial, and I don't know how to factor a polynomial with 5 terms. So we're going to have to break it down another way, and the rational zeros theorem helps us do that. So once again, my a sub n, we're going to find all the factors of a sub n. That's going to be represented by our q here. And a sub 0, p is going to represent all the factors of 9. So let's start off with all the factors of 9. So all the factors of 9 are going to be basically just plus or minus 1. We've got plus or minus 3, plus or minus 9, and we're done. Awesome. And then for the q, plus or minus 1. Let's write down all our possibilities. Plus or minus 1, plus or minus 3, plus or minus 9, and that's it. That's it. Those are all our possible simplified ratios that we can get when we have our p over our q's here. So basically we've got 1, we got negative 1, we got positive 3, we got negative 3, and we got positive 9, we got negative 9. 6 possibilities for our rational zeros. We're going to have to just try them all until we find one, right? We come across one. Let's start off with 1. So we're going to find f of 1 and hope that it's equal to 0. And if not, we just move on to the next one and we try f of negative 1. And then we try f of 3 until we find a 0. So f of 1, once again, like I said, you could just go ahead and put this into your calculator to make life easier on yourself, because it saves a lot of time if you just plug this into your calculator, right? Am I right? Right? So use your calculator for stuff like that, right? Okay, f of 1, if we go ahead and work all this out, simplify this out, I guess I'm just going to show the steps, for the people that need to see the steps. I think there are some people who like to work this out by hand or who do not like to use the calculator. So I'm just going to go ahead and show that for those people. I end up with this. This is negative 1. This is going to give me negative 8. Negative 1 minus 8 is negative 9. Negative 9 plus 9 is 0. We found a 0 on our first try. Come on. You can't say that doesn't feel good. That's awesome. So this is kind of a very exhilarating feeling when you get a 0, especially like on your first try like that. You're like, wow, I found a factor right away. So x minus 1 is a factor of f of x. That means I can probably use, because it is of the form x minus c, I can use synthetic division to start breaking down this polynomial function into factors, into factored form. So make sure it's written in your descending order. My c is going to be 1. Write down all the coefficients of your polynomial, right? And then we're going to go ahead and use our synthetic division here. Bring down the 1. 1 times 1 is 1. Negative 1 plus 1 is negative 1. Negative 1 times 1 is negative 1. 9, 10 minus 1 is 9. 9 times 1 is 9. And negative 18 plus 9 is negative 9. And negative 9 times 1 is negative 9. We get a 0. Yes. This has to be a 0 because we got a 0 here at the end, right? And if you got a 0 up here for f of 1 equal to 0, then you better get a 0 here for this number when you're using synthetic division, or else that means you made a mistake if you don't get a 0 for both of these. All right, so I'm going to go ahead and write down the polynomial that's left over here. X cubed minus x squared plus 9x minus 9. And remember, we have a factor of x minus 1. So if I multiply these together, I'll go back to my original polynomial. So this is f of x is equal to x minus 1 times this polynomial. But I want to have this completely factored out. I don't want to forget my x minus 1, so I'm just going to draw like a little squiggly line with x minus 1 down there. And I'm going to focus on this polynomial with 4 terms. Let's try factoring by grouping. So it looks like I can factor out an x squared out of those two, and a 9 out of those two, and then an x minus 1. And I get x minus 1 times x squared plus 9. All right. Now this is the sum of 2 squares. So we cannot factor out the sum of 2 squares. If it had been a minus sign, then yes, right? But it's a plus, so that will not factor. So I've got the factored form of f of x. Here it is, x minus 1. F of x is equal to x minus 1 quantity squared times x squared plus 9. I'm going to set each one of these factors equal to 0 and try to solve them. For the first one, I'm going to get x is equal to 1. The second one, x squared plus 9 equals 0. If I subtract 9 to both sides, I'm going to get x squared is equal to a negative 9. And if I try to take the square root of both sides, we have a problem here because we have a negative inside of a square root. This is going to give me plus or minus 3i. That's an imaginary number. But the instructions said they only wanted real number solutions. I cannot have any imaginary numbers. So my only real solution for this problem is going to be, yes, you guessed it, x equals 1. Let's go ahead and box that in since that's our answer. Or we could also write it in the form of a solution set. Awesome. Cool. So this is pretty cool, right? We found our solution. All right, I think I'm done. I don't think I can do anymore. There were no more problems for this section, right? This is 5.7, good. So we're not going on 5.7, we're just doing 5.6, and that's it. We did everything on here. So look over this and make sure you understand the steps we did for this problem, and hopefully you feel like this wasn't too bad. This was pretty cool. All right, good job, everybody.